and shrink them vertically or again horizontally. And we might even have a sequence of transformation. Sequence being more than one. We may want to take a function. Maybe a function is defined as f of x is some constant. We may want to shift that constant up 4 units, or we might want to shift it down 4 units. And we'll go in and do some examples of these. But those are some of the objectives then that we want to cover in this section 1.6. So let's take a look at what some of the common functions or frequently encountered functions are. Frequently encountered functions. We might have f of x, y equals f of x equals a constant as shown earlier. We might have y equals f of x and maybe it equals x. We might have f of x equals absolute value of x, where these vertical bars represent absolute value. If you go into your calculator and go into the catalog, you'll see an absolute value function, and that represents this. You might see an f of x that is an x squared. You might have an f of x that's a square root. Lastly, we might have, in terms of the frequently encountered, we might have an x cubed and a cube root of x. So these are what are commonly called the frequently encountered function. Let's see if I can focus this a little bit better here for you. Everybody see that okay? So frequently encountered functions, the ones we're going to talk about are constant, y varies directly with x, absolute value, squared, square root, cube, and cube root. So let's just take a look at some of those functions and see what they look like. So if I have f at c, f of x evaluated at c, and this is called a constant function. And I think the function is fn. And if we were to graph something like that, we would see that if we have x and y in a coordinate plane, and here's our origin, and if y, and I'll make y equal function of x, that were a constant and c was positive, we might have a line that looks like that. Let me just make this up. Sort of looks like that, where this distance in the vertical direction is c. So this point here would be 0 and c, wouldn't it? And that's the function y equals c. It's just a constant value. If c were negative, we might be down here at 0, negative c, and we might have a line that went through that. Maybe it looks like this. Okay, so we're just saying that no matter what x is, y is the same value. Y is a constant value. Okay, questions on that at all? Now, if I were to ask you for the domain and range, and then from our previous discussion, whether this is an even, odd, or neither function, let's see if we can address these concepts with this constant function. So x goes positive direction and the negative direction. And if I were to list this function as shown here in the blue line, what do we think the domain of that function would be? And maybe we ought to define domain to make sure we're all thinking the same concept here.
Negative infinity and positive infinity.
Okay, so it can go on forever in the positive direction and the negative direction, can it? So we might say positive and negative infinity. And then what kind of a bracket or brace or paren, or what would I put around those values?
Parentheses.
Parenthesis, okay, because we never reach those values, do we? How about the range of this y equals c function? What would I call the range on that one?
C.
Just c, isn't it? It's just, that's the only value that this function has. Okay, and then lastly, what I call this an even or odd or neither, and how do I define even, odd, and neither? If I say even, if I say odd, and I say neither, how, before I even answer the question, how would I define an even function? Remember? If we have some value out here, x, let's say I have a value here, x, and here out here a negative x. And at x, the value of this function is this value here, isn't it? So here's x, here's f evaluated at x. Here's negative x. And here's the point f evaluated at negative x. So for this y equals c function, remember that for an even function, we said that f evaluated at negative x equals f evaluated at x, meaning this distance is the same as this distance. Remember that? And then for an odd function, we said, well, f at negative x equals negative f evaluated at x. So if this is the positive value, then here is the negative value. So if we have a point down here, f evaluated at negative x, here, this value in the negative direction is this value in the positive direction. So the magnitudes are the same, only the signs are different. And then neither would be if we had a situation where f evaluated at negative x does not equal either one of these. It's not equal to f evaluated at x, and it's not evaluated at negative f evaluated at x. It's neither one of those. Okay, and we can take a look at some of those values as well. Does that ring a bell that we've gone through that before, everybody? Questions on that at all? Okay. So if that's the case, then what would we call this y equals c function? Let's have some new volunteers. Desiree, Ella, Ferris, any of you guys?
Would it be odd?
Odd. Well, this blue function here. So if we evaluate it at x, we get this value here. Let's say it's 1. Say that's 1 unit. When we evaluate it at negative x, what do we get? We get 1. We get 1 again, don't we? It's positive. It's evaluated at negative x, but the value of the function is still 1.
Right.
Okay, so we're going to say if the value evaluated at negative x is the same as the value evaluated at x, we're going to call that even. So we're going to call this an even function. Okay, makes sense to everybody? Now, if I had something,
Yes.
if I had something that went like this, maybe I'll give that a different color here. Say I had something that went more like that, where here's a function evaluated at x is this value, and the function evaluated at negative x is down here. Then I'm going to say, well, that green function, I'm going to call that an odd function because here's the positive value. And evaluated at negative x, it's the same magnitude, but the direction is the opposite, isn't it? So we're going to call that an odd function. And then if we had some function that did neither, and we'll take a look at that in a bit, it was neither even nor odd, then we're going to say, well, we're just going to call it neither. Okay. Questions on that at all?
Could you explain like that green line that you drew out again?
Yes, the green line is, that might be something that looks like y equals x. The green line might be a function that's defined as y equals x. And if I were to ask you, is y equals x an even or an odd function, you could say, well, let's see, let's create a table of values. Here's x, here's y. And I might put up three values. I might say -1, 0, +1. And if I evaluate this green function at 0, I get 0. Evaluate the function at 1, and I get 1, and -1, I get -1. So then I say, well, what's f evaluated at -1? That's this value here. That's going to be equal to -1. And negative f of x, that's negative of f of this, which is +1. So that's going to be -1 again, isn't it? So we have f evaluated at -x is -1. And f evaluated at x is +1, but we multiply that by a negative. So we get -1 equals -1. Therefore, that's an odd, that's defined as an odd function. We just evaluate the function at a positive x value and a negative, same magnitude, but negative. Questions on that at all? Okay. All right, let's take another one then. If we have this function that we said y equals f of x equals x, and we were to say what's the domain and the range and even or odd or neither, and we're looking at the green function here, f y equals f of x equals x, that's this green line. What would we say is the domain of this function? Can we get a new volunteer? Hudson, do you have anything for us, or Jacob or Joseph?
I'm not sure, Professor. Is it -infinity to +infinity?
To +infinity. Well, are there any restrictions on x for y equals x as x gets large? Is there any restriction on this function as x gets very large? There isn't, is there? So we could say, well, it heads out into the positive x direction for as far as we want to go. And how about going to the left in the negative direction? Well, this line extends in the negative x direction as far as we want to extend it. But we never reach negative infinity, so we're going to call that a bracket.
Okay.
Okay. Now, same way, let's look at that function and see if we can come up with a range. So do we have a new volunteer that can give us the range of the green function, which is y equals x, this function here?
It
And
will
I'll
be infinity to +infinity because the line continues, the domain continues infinitely, so the line will also continue infinitely, so the range will also be.
Okay, so it continues without limit in the positive y direction and in the negative y direction. Okay, and then lastly, based on our definition above, would we call this an even or an odd or a neither type function? New
Would it be,
volunteer.
would
Go
it be odd?
And it looks like it would be odd, wouldn't it? Because f evaluated at negative x here is the opposite value of f evaluated at positive x. So we'd call that an odd function, wouldn't we? Okay, is that making sense as we go through and make these definitions? Questions on that at all?
Could you explain why it's odd again?
Yes,
That's based out there.
yes. If we evaluate the function at x, we get this value here. And let's say that value is 1. So we have 1, 2, 3. Let's call this point 3 and 1. And over here, negative 1, negative 2, negative 3. So here we're at negative 3 and negative 1. So if I evaluate the function at x, I get 1. If I evaluate the function at negative x, what do I get? Negative 1, right? It's down here. So negative 3, it's negative 1. At positive 3, it's positive 1. So f at negative x, so f at negative 3 is negative 1. And f at positive 3 is positive 1. Okay, so f at negative 3, that would be this situation here. F evaluated at negative 3 is negative 1. F evaluated at positive 3 is positive 1. And if we take the negative of that, we get negative 1. So F evaluated at negative 3 is the same as the negative of F evaluated at 1. So here's F evaluated at 1. Here's F evaluated at negative 1. They're opposite. We call that odd. Okay, questions? Okay, let's try another function. One of the common functions. Let's say we have y equals function of x, and we call it the absolute value function, ABS of x. On our calculator, we would have ABS, wouldn't we? And so if we were to graph this, well, how would we graph it? Well, we could set up a table of values. We could say here are the x values. Here are the y values. And maybe I'll graph 3 or 4 points, whatever. And I'll have one of the points as 0. And so when x is 0, what's y going to be? Christopher, what's y going to be?
0.
Are you Christopher?
My bad.
No, no problem. I just want to have everybody get a chance here to make sure everybody gets an opportunity. So if x is 0, the absolute value of x or y is 0. Well, maybe if I have x as positive 2, then the value of y is going to be the absolute value of positive 2, which is just 2, isn't it? And if I look at x at negative 2, if I put a negative 2 in here, what's the value of y? Go ahead, Paul. Go ahead, Paul. Paul doesn't want to go ahead. All right, who else wants to go? Go ahead. What's the value of y when x is just positive 2, isn't it? We're not concerned with direction here. So if I were to plot these 3 points, negative 2, positive 2, here's 0, this is x, this is y. At negative 2, I'm at y is positive 2, that's this point. There's negative 2, 2. And here I'm at 0, 0. And here I'm at positive 2. and 2. Now, from just those 3 points, that could be a parabola, or it could be a, who knows what that could be. So let's plot one more point. Let's say -1 and +1. Let's plot a point at +1. Well, at +1, we're going to still be at 1 here for y, aren't we? So we're going to have a point here at 1 and 1. And back here, we're going to have a point at -1 and 1. So it looks like our graph is going to go like this. If I were to show you that graph in a blue color, it would look sort of like that, where it continues in the positive x direction and the negative x direction, and this is a straight line. Okay, so when we look at the function y equals absolute value of x on your calculator would look like this. So if we had to plot that over various values, we're going to see a line that comes from upper left down to 0, and then from 0 goes to upper right. And so then what we've asked for previously is, well, do we have a domain? Do we have a range? Is it even, odd, or neither? And we might ask one other thing about here. Where is this function decreasing? And where is it increasing? Over what interval? So let's see if we can go through and systematically answer some of these questions. So if we look at the domain of the y equals absolute value of x function, can we tell from the graph here what that domain might be?
-infinity to +infinity.
Okay, -infinity to +infinity.
So on the
We
test,
don't reach those values. Yes, go right ahead.
yeah, so on the test, if we are asked the domain, how do we show our work, or do we just write the domain?
I think you can write the domain here. You can show your work by showing a graph of the function, and you can show an arrow at the end of the function, arrow indicating that the function keeps going in that direction and keeps going in this direction. That's what that arrow would indicate. So I would graph it. I would label the x and y coordinates. I would label the various hash marks that you put along the x and y axis, and any points you put on the graph, be sure you label those points. So if this is point 1 and 1, and that's point -2 and 2, and this is point +1 and +1 and +2, +2, I would label your points rather than just say, oh yeah, it looks sort of like this and looks sort of like that. I want to see a little more detail in terms of you showing me where the points are and labeling your points. You could also say then y equals absolute value of x and say, that's that curve here. It looks like this.
Okay, thank you.
Sure. Now for range, we've got the domain on here. How about the range?
0 to +infinity.
0 to +infinity. We know this is going to be a right paren. How about on the left here? Is that going to be a left paren or a left bracket or a left brace, or what's that going to be to accurately describe that?
Wouldn't it be a
A bracket.
A bracket like this?
The other way.
The other way. Okay. So you want it going like this. And that means what when you put that bracket there?
That it includes 0.
That it includes that point. That's right. Okay, it includes that point. So the range goes from 0 on up, and we're showing the domain. And if we said, where is the function decreasing? Where do we think that from what to what is the function decreasing? Can we have a new volunteer? Ferris, you with us? Jacob Jr.?
Yeah, I'm with you.
Yeah, go right ahead. Can you let me know where you think this function is decreasing?
I'm not sure. Sorry.
All right, no problem.
I think from negative infinity
So it's decreasing from x is negative infinity to where?
to 0.
To 0. Okay, so from anywhere out here, x is large negative number to 0, and we don't include negative infinity, so I'll put a parenthesis there. How about the 0? Do we include the 0?
I want to say no.
You'd say no?
I think
And why would you say no?
well, would you put the bracket because with for the positive at infinity, it also starts from 0, so wouldn't we use the bracket?
All right, if we take a look at points on this line and we put a line through the point on the line, when we get down to 0, at 0, that's horizontal, isn't it? That's the x-axis. So we're going to say it goes down to 0. It's decreasing to 0, but when it actually gets to 0, it's going to be horizontal. So we're going to say we don't include the 0. And similarly, if we're increasing, we go from 0 out to positive infinity. All right. And then we have to decide whether we're going to include that 0 or not. And I think we'll use the same rationale we did above, which says we're not including the 0 because at 0, we're horizontal. We're coming down, down, down until we get to 0. Then we're horizontal. Then when we start back up, anything greater than 0, we're now going back in the increasing direction. Okay, and then lastly, is this function even or odd or neither? What are we thinking? How would we determine that? Is it even, odd, or neither? And more importantly, how do we determine whether it's even, odd, or neither? Well, we can pick a point out here, can't we? Say f evaluated at 2. So f evaluated at 2 is, let's 2. And then we evaluate f at negative 2. And what do we see here? F at negative 2 is still 2. So when we had f evaluated at negative x equals f evaluated at x, what did we say that function was?
Even.
Even. We said it was even, didn't we? We said it was even. When these points are the same in the wider, then we're going to call that even. Okay, good. So we've taken a look at the y equals absolute value of x function. We evaluated it from negative 2 to positive 2. We plotted the points, labeled our points, determined the domain from negative x large or negative infinity to positive x large or positive infinity, took the range from 0 and including 0 up through y goes to positive infinity. Based on our definition of even, odd, or neither, we said that when the function evaluated at negative x equals the function evaluated at positive x, when they're the same, we call that even. And we said it's decreasing from negative infinity to 0 and increasing from 0 to positive infinity. So we pretty much labeled this function and said everything about what we want to know about that function. Okay, another common function then. All right, questions before we move on?
Could you explain how you got the decreasing thing again?
Yes. Decreasing when x goes from any large value in the negative direction. So anything out in here would be negative x, and negative x could be large, any large value we wanted to make it up to, but not including infinity, because we never reach infinity is not a number, is it? We just keep going larger and larger and larger in the negative direction. So as this line moves farther and farther in the negative direction, we never reach it, but we just say then it's heads out that direction. And from way out there, as we go to the right, it's decreasing. Okay, here it's decreasing, and it's decreasing until we get to 0. It's always decreasing. At -1, it's decreasing. At -0.5, it's decreasing. At -0.1, it's decreasing. At -1,000th, it's decreasing. But when it gets to 0, it's no longer decreasing. So we don't include the 0. Does that help?
Yeah, it helps clear some stuff more. Thank you.
Okay, good. Okay, let's take another example. Let's say we have a commonly used function that's y equals some function of x equals x squared. So it's a standard quadratic function. And if we were to graph that, you'd say, well, now one of the things you're going to want to know and keep in your brain is, what do these common or frequently used functions look like? F equals c, f of x equals x, f of x equals x squared, and so forth. So if we take a look at this, if we don't know what that looks like, first we might say, well, let's create a table of values of x and y, and maybe we'll go out a few, maybe we'll -2, -1, 0, +1, +2. And we might want to graph these the first time through until we know what y equals x squared looks like. And here's our origin here. So when x is 0, that's always an easy one. So x is 0, y is 0. So it looks like we're here. Now if we say x is 1, +1, +1 squared is still 1, isn't it? If I go out here, 1 and 2, 1, 2, 1, 2, 1, 2. Okay. And if I go out to +2 for the x value, 1, 2, I'm going to go up 2 squared, which would be 4. 1, 2, 3, 4. So let's say that's approximately here. So 1, 4. So we've got values that 1 and 1 would be a point here. 2 and 4 would be a point here. And if I label these points, that's 0, 0. Here's point 1 and 1. Here's point 2 and 4. If I had a 3 out here, what would the value at 3 be? Three and 9, wouldn't it? 3 squared, 9. That's way up off the paper. So -1, if we square -1, we still get a 1. So we're still going to get this point, -1 and 1. And if I go -2 and square -2, I get a +4, don't I? So -2, I'm still clear up at here. So here's -1 and 1, here's -2 and 4. And so I'm going to label these points and show you where they are. Okay, and then I will connect them with a smooth curve. So if I come down here through there and then come back up through here, I would look like an upward facing parabola. And it opens upward. And the vertex is at the origin, isn't it? Here's the vertex, it's at the origin, and it opens upward. Okay, so this is a standard quadratic function. Here's what it looks like, and I'll just color that in so that you can see it a little better. And I've plotted my points. I've connected them with a smooth curve. And now I'm going to say, now I know what that looks like. Let's answer the same questions. I want the domain and the range and where it's increasing, where it's decreasing. And is it an odd or even or neither? What kind of a function is it? So the domain, what do we think the domain is going to look like for that function? Do we have a new volunteer on this one? So everybody gets a chance to participate.
I think it'd be 0 to positive infinity.
Domain 0 to positive infinity, like that.
Mm-hmm.
All right. Anybody else?
I think it's negative infinity to positive infinity
And why do you say that?
because the domain is looking at the x-axis and it keeps on going left and right.
Okay, so we can go large negative values of x without bound. So we can continue going this way without bound, and this curve will continue as far as we want to go. And we know it include those values. So let's say that the function is negative infinity to positive infinity. Okay, good. How about the range? We have a new volunteer for the range, which I show as R here.
It's just
Range.
positive infinity.
Positive infinity
Yeah, and then there's 0.
and 0. Positive infinity and 0.
Oh no, to the left. Move to 0 to the left.
Over
Yeah.
here.
Yeah. And
Okay.
then put a bracket for 0 next to 0 since it counts 0. And then there'll
Okay.
be just a regular parentheses for positive infinity.
Okay. All right. That look right to everybody? Everybody agree? And how about where is the function decreasing? From where to where on the x-axis? From clear out here, x is very large. As we move x from left to right, is it continuing to decrease? From x is negative large, and then it continues to decrease until we get to where?
0.
Till we get to 0. And we don't include that 0, do we? Because it's not decreasing at 0. And then it's increasing for where we get greater than 0, which says, we'll put a left paren here, which says anything greater than 0, but not including 0, out to positive infinity. Okay, so decrease, I've got that just the opposite. I better change that then, where I should have put decreasing first. So decreasing left to right, it decreases from negative infinity to 0, and it increases from 0 to positive infinity. Okay, so as we come from the left, it's decreasing. As we move out to the right, it's increasing. All right, now based on our definitions that we showed earlier, would we say this is an even, odd function, or it's neither an even nor an odd function? And how do we define odd, and how do we define even, and how do we define neither?
So I do have a question about that. Can you just pick any point to start to compare or?
Yes,
Okay.
yes, we can pick a point here, anywhere on the right side, anywhere on the left side. We're looking at the same value as we go across here, aren't we? So if we go out 1 on the positive x-axis and go back 1 on the negative x-axis and find out what that point is. Now, I think your question had to do with determining whether it's odd, even, or neither, right?
Correct.
So if we were at positive 1, we evaluate f at positive 1, and we'll say that's 1. Here it is here. And then let's look at f evaluated at negative 1, and that's going to be 1 again, isn't it?
So it would be even.
So that says f evaluated at negative x equals f evaluated at x. And we said that was even, didn't we? So it's an even function because of the way we're defining even and odd. That makes sense to everybody? Questions? Okay, let's try the square root function. Let's say I have y equals f of x equals the square root of x. And I go through the same procedure. And I say I create a table of values and I plot some points x and y. And maybe I go 0. And since I'm taking the square root, let's take something that, well, maybe I'd take 2 and 4. And maybe -2 and -4. So if I say, let's take a look at y evaluated at 0, because we're going to try and plot this thing. If I say y evaluated at 0 is going to be what?
0.
0. And y evaluated at 2.
2.
So the square root of 2 is 2.
No, 4. I'm sorry.
Square root of 2 is 4,
Square root 2.
which is approximately 1.41. And how about the square root of -2? How about the square root of 4?
2.
Square root of -4?
I'm not sure.
Okay, anybody give me the square root of -4? First of all, let me ask, is it on the real number line?
Yes, -2.
The square root of -4 is -2.
I'm going to say yes.
All right, let's test it. So that says -2.
Oh, no, it's
and
positive. It's
-2.
positive.
That's a positive force. So -2 is not the root of -4, is it?
It's +2.
So the root of -4 is +2. So +2 times +2 gives me a -4.
Mhm.
Everybody agree with that? +2
No,
times +2 is -4.
I think it's
it's
undefined.
positive.
Right, it's not a real number, is it? This is an imaginary number, and we're not talking about imaginary numbers right now, but we can't do this. So we're going to say that that doesn't apply because we can't take the root of a negative number based on what we know right now. So we're going to say we can't have anything less than 0 because that would be a negative value. So let's plot the points that we have. 0, 0 is here. 2 and 1.41. So here's 1, 2. So 2 and 1.4, I'm going to say is right there. So that's that point. And x is 4, 1, 2, 3, 4. And y is 2. So it looks like we have 4 and 2, 2 and 1.41, and 0 and 0. If I were to graph this, it kind of looks like this, which I will put here so we maybe see that a little better. So it's going like that. We've got points here at over 4 and up 2, and here over 2 and up 1.41. 1, 2, 3, 4. So this is generally what our curve looks like. And now we want to see if we can answer the same questions. We're looking at domain and range. Where is it increasing? Where is it decreasing? And is the function odd or even or neither? again, based on our previous definitions. Okay, so what do we think the domain of this y equals root x function, y equals root x, and that's that line there? What do we think the domain of that thing is?
0 to positive infinity.
0 to positive infinity. We don't reach that. Now, what do we do with this 0?
That include 0.
Includes the 0. Okay. Everybody agree? Anybody disagree? Okay, how about the range? So here's 0, 0. I guess I should highlight that since we've got that point right there. So what do we think the range of this function looks like? From y equals something to y equals, it looks like there's no limit on how big y can get. So it looks like it goes to positive infinity. But how about on the low end? How low can y get? What's the least it can be?
Isn't it 0
0.
as well?
Still 0, isn't it? So we have a range that 0 to positive infinity. And where is it increasing? Increasing from 0 to positive infinity. And do we include that 0 or not for where it's increasing?
We include 0.
You think we do include 0? Okay. So at 0, we're like we were before. We're neither increasing nor decreasing. But if we're anything larger than 0, 0.00000001, out there, we're increasing. But at 0 itself, we're not increasing. So we're not going to include that. Okay, so the function is increasing from 0, not including 0, to positive infinity. Decreasing, well, as we move left to right, we don't really decrease at all, do we? So we're going to say we don't have that situation. And how about, is the function odd, even, or neither? And remember how we defined them? Odd being f at negative x equals negative f at x. Even f at negative x equals f at x. And neither would be, neither of these cases is true. So what do we think? That is to say, if we apply these definitions to this curve, what are we going to get? F evaluated at 2. So F evaluated at 2 is going to be 1.41 and some decimals. How about F evaluated at negative 2? Doesn't exist, does it? So if we can't evaluate F at negative x, we can't say it's even or odd, can we? Because we can't evaluate it at negative x. It doesn't exist. So we're going to call this neither. Okay, neither even nor odd. Okay, questions? Okay. Now the same thing would apply to the cube values. If I say y equals x cubed or y equals cube root of x, we're going to get similar situation. X cubed, it looks sort of like that, and cube root looks sort of like that. And I'll leave it to you to create a table of values if you want to do that and go through the same logic we did before. There's nothing different conceptually in taking a look at the cube. So what I want to do is look at the next concept, which would be doing some shifting. And we want to shift, we might want to shift vertical or horizontal. Okay, so by shifting vertical or horizontal, I mean the following. If I say y equals some function of x equals some value, and maybe it's equal to, well, no matter what it is, it's equal to something. Y is equal to something, x, y. However I want to define this, might be constant. It might be a constant. It might be c. It might be x. It might be x squared. It might be any of the common functions that we've talked about. But if I shift this value in the vertical direction, I simply add a value to whatever we have here. So if I add, maybe this is C1, if I add constant 2 plus constant 2 plus constant 2, I'm calling this constant 2 because I have a constant sub 1 here. So if y equals some constant, say C1 here, and I add another constant C2, which maybe this is this distance C2, not squared, but C2. So y equals this constant plus this constant. So now the new value is here. We have now shifted vertically by a value of positive C2. I could have made this a negative value and shifted it down. So now we have f of x plus C2 up here. And here we have f of x minus C2 down below. Okay, and then here's just f of x, which is this value here. Okay, so we're shifting whatever the function is defined as. We're shifting it up a constant value, or we can shift it down a constant value. Okay. If, for instance, the curve, if we said y equals something that looked like this, and I could shift, I could say y equals f of x, and maybe that's that. And if I say, what if I shift that down 3 units, y1, y2 equals f of x minus 3. So I might have 1, 2, 3. Here, if I shift this down 3, I'm looking at the same curve moved down that direction. Okay, so this is a shift of -3 vertical. Shifting it down 3. Here's a shift positive C2 vertical. So these are vertical shifts, whether the function is a straight line, whether it's a curve. We're going to shift that value by adding something out here to the f of x.
Could you move the paper down just a little bit, please?
Yeah, down this way.
Yeah, thank you.
Okay, so y equals f of x plus or minus some constant value, where this c is how much we shift. And it could be positive or negative. Okay, questions on that at all? Okay, now we might have, if I said this is f of x and this is f of x minus 3, if I said y3 equals f of x plus 2, I'd say, well, if this is 1, 2, 3, I go up 2 more and draw that same curve, then here's f of x, here's the original f of x, here's the f of x plus 2. Because it takes whatever y value you generate with f of x, whatever that number is, you're going to add 2 to that value. So this y3 will always be shifted up from this y1 value. And down here, this y2 value is always shifted downward by 3 because of the way we defined it right here. Okay, so here's a downward shift, here's an upward shift. Both vertical, one's up, one's down. Okay, questions?
So in this case, how does like y squared or like regular y, how does that affect like how the chart moves? That makes sense.
If you had a y squared function,
Yeah, versus just like a y.
the y squared function remember, look like that. Y equals x squared. We said it was an upward facing parabola. If I said y equals x, so that's what this is. If I said y, that's y1. If I said y2 equals x squared plus 3, 1, 2, 3, and I would draw that same curve.
Oh wait, I thought y2 was y squared. That's why I was confused. I was like, what
No,
effect do?
no, that's y sub 2.
Okay.
Y squared looks like that. Y sub 2 looks like that. That's a different y.
Okay,
This is
my
the
bad.
square. That's the square of y.
Yeah, I got confused in that part. I
All right.
understand now.
We might have a y sub 1, a y sub 2, a y sub n. A lot of different values of y. Okay, we might have an x squared or root of x or x cubed. Different y's.
Yeah,
Just a different y.
I got confused. Sorry.
Okay. Right. Any other questions? I'm going to take another example. Let's say, and let's see what would be a good example. What time do we have here? 3:57. Let me do one more example that shows you an example of stretching. If I have y equals a function of x, and it looks like absolute value of x, and I plot that, and I say table of values x and absolute value of x. So y equals this absolute value. So if I plot from -2, -1, 0, 1, 2. So if I plot this at 0, it's 0. At 1, it's 1. 2, it's 2. -1, -2, right? Just the absolute value. Now, if I say, well, I want, that's y sub 1. Y sub 2 is 2 absolute value of x. And we're asking, what does that look like? Well, at 0, if the absolute value of x is 0, 2 times 0 is still 0, isn't it? So they start at the same point. If I say x is 1, so this value becomes 1, which is shown here, times 2 is 2. If x is 2, absolute value of 2 times 2 is 4. Okay, if I go back to here to -1, absolute value is 1, multiplied by 2, I get 2, and similarly here, I get 4, don't I? So let's plot those two values and see what they look like. So here's x, here's y, and I'm going to go up 4 in the y direction, and I'm going to put 4 hash marks in the x direction. 1, 2, 3, 4, -1, -2, -3, -4. At 0, and I'll plot the y1 first. 0, 1, and at 2, I was at 4, so here's -2, and here's at 4. And these were straight lines. Those are meant to be straight lines. There's no square value in here. That's just the absolute value. So there is y1, y sub 1. So now we want to ask ourselves, what does y sub 2 look like? Let's see, 0, 0 at 1. Oops, that didn't draw that right. At 1, it's 2. It's up here. Now, let me draw a better graph. Let me get out some graph paper and do it properly here. So let's say I have here, and I'm plotting my table of values, and I said my table of values for x. I have 4 o'clock. I will continue this after our break. So can we get by with a 5-minute break? Is that enough for everybody?
Sure.
Yep.
Yes.
All right, we'll see you in 5 minutes.
Your mic is mute.
Are we all ready to come back?
Yep, it's 5 minutes.
Okay. If we're all back, let's go ahead and start. So here I'm graphing x and y1 equals absolute value of x, and y2 equals 2 times the absolute value of x. And here's the blue curve is y equals absolute value of x, and the pink curve here is y equals 2 times the absolute value of x. And you'll notice that in the first case, we go over 1 and up 1 because we're just substituting a 1 in here. In the second case, when we substituted a 1, we multiply it by 2. So we're stretching in the vertical direction. This is the stretch. So here's the original. And then when we stretch it, we increase the vertical distance. So that's what we mean by stretching. If we were to make the value, the multiplier out here, greater than 0 but less than 1, we'd be shrinking. For instance, if I said y sub 3 equals h of x, and that equals 1/2 absolute value of x. So if x is 4, half of that is 2, so we'd be out in here. And -4, we'd be at 2, be out in here. So now our graph is going to look like this and like this. And we might have a different, let's see, let's just make this color here. So I might have something that goes like that. And I'm going to say this then is the stretch, where this one is the shrink. I'm making the vertical value smaller. Here's the original vertical value. Here's a smaller vertical value. Here's a larger, the pink line is a larger vertical value. So I'm saying I've got original, I have a stretch and a shrink. Okay, and we can do that with curves that look like that. We can do it with curves that look, say we have a curve that looks like that, and we can stretch it to a curve that looks like this, and we can shrink it to a curve that looks like that. So that would be shrinking. Here would be the original curve, and here's the stretch curve. Okay, everybody okay with that? Everybody see what we're doing there? We're just increasing or decreasing the vertical value. So that's stretching and shrinking. We can also move things around. We could say, well, what if we started out with a, let's say we have a parabola. And maybe we have a parabola where we start here, 1, 1, 2, 4. So maybe we have a parabola that looks sort of like that. And that might be the curve y equals x squared. And we might want to shift that curve. Might want to shift it. We might want to, we might want to shift it what? Horizontally. We might want to shift it vertically. We might want to stretch it. Several things we could do to that curve. Well, if I say this is the curve y equals x squared, and I say, here's what I want you to do to that. I want you to create, maybe that's an f of x. I want you to create a g of x, which looks like the original curve, but it's stretched, it's shifted right, and it's shifted vertically up. So here's the vertical shift, here's the horizontal shift, and there is the stretch. This increases the value of what's in the parenthesis here. So if it was just x squared, it would go up and look just like this. but we're going to make it 2 times this, which means that when we go over 2, instead of going up 4, we're going to go up 8. Similarly, this says we're going to add 3 to whatever value that is. So if this says we go up by 8, we add 3 to it. So now we're going up by 11 for every value of x. And this -1 here says we're going to shift this curve to the right. So let's just draw what the shifted curve would look like. So it's going to be to the right 1 value, up 3 values, 1, 2, 3. So now the vertex, instead of being at 0, 0, is at 1 and 3. So here's where the vertex has shifted from here to here. Okay, and how do we do that again? Here's the vertical shift. Here's the horizontal shift. And I'll ask you to create your table of values so that you can plot these points. Plot the original x squared, plot, if you call this f of x, call this g of x, and plot the points for this. And you're going to see that the vertex goes to here. And then we're going to have a curve that is, because it's multiplied here, we're stretching it, which means that this curve is going to come in. So it's going to be narrower than this curve here because of this 2. Okay, so the -1 shifts it to the right 1, and this +3 shifts it up 3. So here's our new vertex, and this 2 says we're going to stretch it, which pulls these values together. These sides of the parabola get closer together because they're increasing more rapidly. Okay, so if I draw this one in, let's say I draw this in blue, then I could draw this one, say, in an orange value here, and it would be shifted up and closer together. Okay, so that's what we're talking about when we're doing stretching, shrinking, when we're doing shifting left and right. Okay, before I go to the next section, I'll stop and ask for questions on anything we covered in transformations, which was section 1.6 here.
Wait, so what does it 2 do again?
This 2?
Yeah, what does that do again?
Well, keep in mind, say we just had y equals x and y equals 2x. What does this 2 do? It increases the value of in the y direction by a multiple of 2, doesn't it? So if x is 0, this is still 0. If x is 1, this is 2. X is 2, 4, 3, 6. And we could find that by looking at our table of values, couldn't we? X is something, y is x, and y is 2x, and y is x squared, whatever we want y to be. It'll be some multiple of whatever we put here. And that's called a stretch value because it makes it larger. If I said y equals 1/2 x, then the y value would be less than the x value, wouldn't it? It's only half as much. So here it's twice as much. Here it's half as much. This is a stretch. This is a shrink. One's larger, one's smaller. Other questions? Okay. Let me go to the section 1.7, which is our last one that we'll cover today, combinations of functions and composite functions. Composite functions. So let's take a look at what some of those might look like. So let me get out a clean piece of paper here. And like we've done before, we want to be able to find the domain. And we want to be able to combine, in this section, we'll be able to combine functions. I'll show you how do we do that. We want to be able to form a composite functions. I'll show you how to do that. All right, so let's go through some examples here. let's say I have a function that looks like the following. F of x equals, and I give you x squared plus 3x minus 17. And I ask you for the domain. What would you give me for the domain for that function? Anybody? Let me set up a table of values for x and f of x, which we'll call y. If I said x is 0, what are we going to have for the y value? This is 0 squared, so that's still 0. 3 times 0, that's 0. So we're just left with negative 17, aren't we? So if y equals some function of x, then, and we set that function x squared plus 3x minus 17, we'd say that. If we said x is 1, you'd say, well, 1 squared is 1, plus 3 times 1 is 3, minus 17, so 17 minus 4, that's going to be 13, isn't it? Okay, and then x gets some large number. Say x is very large, then x squared is very large, 3x is large, subtract 17, we're still going to have a large number out here. And if x gets very large and goes out towards infinity, anything stopping x from going to infinity? So we could say, well, then the domain of this thing is x can go out to positive infinity. How about negative direction? Anything limiting x in the negative direction? Negative x squared plus 3 times negative x minus 17. Anything limiting what x can be? There isn't, is there? So we're going to say then the domain of this function given here is negative infinity. X can go from negative infinity to positive infinity. Okay. It's a set of all real numbers. Okay, makes sense to everybody? All right, let's try a different one. Let's say you're given g of x equals 5x, and let's say it's divided by some other value, x squared minus 49, let's say. And we ask for the same thing. That is to say, we're asking for the domain of this function here. And remember where we put limitations on the domain. Remember we said, well, we've got a denominator here. We can't divide by 0, can we? So we better figure out what values of x, if any, would cause this value to go to 0. So the numerator remains 5x. If we factor this denominator, what does it factor into? If we factor x squared minus 49, what do we get?
X and 7.
X plus 7 and x minus 7.
Correct.
So if these things are set to 0, x plus 7 equals 0, or x minus 7 equals 0. So x equals negative 7. We can't have that because that would cause this denominator to go to 0. And if we had x equals positive 7, that would set this value to 0 and the denominator go to 0. So we have to exclude these values, don't we? We've done that before, haven't we? So we're going to say then in this case, x can go from negative infinity to positive infinity, but we have to exclude these values, don't we? Okay, does that make sense to everybody? Okay, so if I were to draw this on the real number line, I guess I could say here's 0, here's positive, here's negative. So we'd say, well, it goes from negative infinity. And when we get to -7 right here, we can't include that. There's -7. Here's +7. We can't include that either, can we? Okay, so we could have a value that's larger in the negative direction, but we can't have -7. So we're going to say, well, it can go from negative infinity to -7. That's acceptable. Anything out in here is acceptable, and anything out in here is acceptable, isn't it? So we could say could be from 7 to positive infinity. Now, how about in here? What can we say here? Well, let's see. As long as we're not -7, so anything greater than -7, not including -7, up to +7, but not including +7. We can't include these values, can we? Because those values would cause that denominator to go to 0. So we can go -7, negative infinity, -7, or, that's the symbol for or, something greater than -7 and something less than +7, or +7 to positive infinity. Okay. So that's quite a bit different when we have a value in the denominator. We have a quotient value here. First one, we didn't have a quotient. Second one, we had a quotient. So whenever we do that, we're going to have to be a little more careful, aren't we? Okay, questions on that at all? All right, let me try another example here. If I say, let f of x equal x minus 5, and I let g of x equal, let's say, x squared minus 1. And then I say find the following. Let's say find f plus g of x. Are we able to find f plus g of x? So let's see, what would we do? This just says take f of x. So that's really equal to f of x plus g of x. We're taking x evaluated at f and adding it to f evaluated at g. So, or x evaluated at g. So x evaluated at f, x evaluated at g. Two different functions. And we can represent it this way, or we can represent it this way. F plus g evaluated at x. And now we're given the two functions, x minus 5 and x squared minus 1. So if we add those together, so f of x is x minus 5. There's f of x. And to that, we want to add the g of x, which is x squared minus 1. Okay, so now if we combine those and keep in mind what the exponents are, we've got how many x squares? Well, just 1. Plus how many x's? Looks like just 1. And -5, -1 gives me a -6. So we're going to say then that f plus g evaluated at x looks like x squared plus x minus 6. So that's what that function would look like once we combine those functions, add them together. And so if I ask you what the domain of that is, you'd say, well, what are the limitations on what x can be? Well, in the negative direction, looks like we could go all the way out, in the same way for positive. We can go all the way to the negative infinity and all the way to the positive infinity. Nothing's going to change. This -6 is just subtracted from what we have here. Okay, questions on that? you have questions, be sure and ask. Let's say I have f minus g evaluated at x. What is that going to look like? Well, let's see, f minus g, f is x minus 5, minus g, negative x squared, negative 1. So that's x minus 5. Negative times a negative is a positive. Well, this isn't negative x squared, is it? G is just x squared. So I'm not going to put a negative x squared there. I'm just going to put x squared. Okay, so be careful when you write these out. Negative x squared, that's negative x squared. Negative times a negative is a positive 1, isn't it? So I can simplify f minus g evaluated at x equals negative x squared plus x, and negative 5 plus 1 is negative 4. Okay. Questions on what we did there? And then if we're looking for the domain, what do we think the domain is going to be here? Any limitations on what x can be?
No.
Okay, so we go from negative infinity to positive infinity again, wouldn't we?
Professor, how do we determine if there are limitations or not?
Well, when we had a quotient, remember when we had a quotient, let me bring this one back. Remember when we had a quotient here and we knew that we can't divide by 0? So we said, well, if any of these are equal to 0, then we have to exclude those values. So we said x plus 7, set that equal to 0, and x minus 7 equal to 0. And we excluded any value that causes the denominator to go to 0.
Okay.
Make sense?
Yeah, thank you.
Okay. All right. Let's see. What if I have a situation that says f times g of x? So that's the same as f of x times g of x. And f of x, x minus 5, and g of x was x squared minus 1. All right, so let's go ahead and expand that. Tell me what you get. That's f times g evaluated at x. So go ahead and do that for me, and then open your mic and step me through what you did. One of the things I want you to be thinking about as you do these problems is how long it's taking you to get through these problems. And I would expect the first time through, it's going to take you longer than after you've done your homework and you've done a bunch of these problems. Because remember, at test time, you're limited on how many minutes you have on each problem. If you have 10 problems and 30 minutes, 3 minutes a problem. So you want to make sure that ideally when you take a test, the questions won't be unfamiliar to you because you've done all your homework. You've done your studying of the sections that we've covered, done the homework problems. And when you look at a problem on a test, you should be saying, oh yes, I know how to do this because I've done several of these in the homework. And then it's just a question of I can solve this problem as quickly as I can write. That's what I'd like to happen. Now, if this is the first time you've seen these kinds of problems, it's going to take you longer. But you have done this before. This binomial times this binomial. And we foiled that, didn't we? So what did you guys get when you foiled x minus 5 times x squared minus 1? What did you guys get on that?
I have an answer.
Go right ahead.
Okay, so I got x cubed minus 1x minus 5x squared plus 5.
Okay, anybody else?
I agree with that.
Okay, now generally we're going to put these in descending order of exponents, aren't we? So we'd prefer to see this as x squared minus, I guess, x cubed minus 5 of the x squareds minus x to the 1 plus 5, and that's really x to the 0, isn't it? X to the 0 is 1. X to the 3, x to the 2, x to the 1, x to the 0. So this would be the preferred way we would show this. And we put a box around it, put a left arrow to it, put an A and S there saying that's where I'm going to look for my answer. And then I can quickly go here and say, there's where the answer is. Yes, that's the correct answer. If it looked like this, then I've got to take some time and figure out what was what. So that may not add in your favor if I go through here and think, oh, it doesn't look like what this looks like. And grading 2 classes and multiple students, there might be a cause for error here. So please put them in descending order of exponents, okay? Make sure you get all your points. So if I were to do this f times g of x, and let's say, oh, what's the domain of f times g of x? What would you tell me on that?
Domain is negative infinity to positive infinity because there's no limitation.
Okay, everybody agree? Anybody have something different?
I agree.
Okay, and we would put that like that. Okay. Okay, good. And let's see, do I have room on this page? I guess I do. Let's say I have f divided by g of x. And we say that's the same as f evaluated at x over g evaluated at x. And let's see, they were given as, give that f of x is x plus minus 5, x minus 5 over x squared minus 1, x minus 5 squared minus 1. So I'm evaluating f divided by g of x, which is the same as this over this. Can everybody agree with that? And then is there some way I can simplify this or not? And any exclusions? Now, let's see, we probably want to factor this if we can, factor the denominator. Does that look like a square minus b square? And if it does, how does that factor?
X plus 1 and x minus 1.
Okay. So we say f over g of x equals x minus 5 over x plus 1, x minus 1. Okay. Any exclusions? New volunteer.
X cannot equal plus or minus 1.
All right, that's good. So x cannot equal 1, x cannot equal negative 1, because if we set x plus 1 to 0 and solve, and x minus 1 to 0, we get x equals negative 1 as an exclusion because it causes the denominator to go to 0. And x equals positive 1 as an exclusion because it also causes the denominator to go to 0. So we say here are the exclusions. Here's what we get when we solve. And how about the domain? Can we say what the domain is? Say here's a Real number line from negative infinity to positive infinity. And maybe here's arbitrarily, we'll put a 0 here. So we're going to exclude positive 1 if that's 1, and this is negative 1. We're going to exclude that. We're going to exclude that. So we're going to say we can go from negative infinity until we reach negative 1, but we can't include negative 1. Or we can go from negative 1, not including negative 1, to positive 1, not including positive 1, or positive 1, not including the 1, to positive infinity. Okay, so if we were to draw that out, I guess we could say it kind of goes here and here and there. But we can't have values at here and here, can we? Does that make sense to everybody, what we're doing there? Questions on that at all? Okay. I'll take that as a no. Let's see if we've got any more values that we can take a look at here. If we let some function of x equal root of x minus 3, and maybe g of x equals root x plus 1. And I ask you to find f plus g of x. Are we able to do that? So we said that was equal to f of x plus g of x. And are we able to combine these values, x minus root x minus 3 and root x plus 1? Are we able to combine those? So f plus g evaluated at x equals f of x, which is root x minus 3, plus g of x, which is root x plus 1. We really can't combine those, can we? Those are two different things.
No, I don't think we can combine it.
Okay, so let's just leave that alone for a minute. And we think that's what our answer is. Now, if I come back and ask you for the domain of f plus g evaluated at x, I'll take that out. Can we say what the domain of that is?
Would be 3.
And for what reason are we saying 3?
Oh, I'm not sure. I'm not sure.
Okay. So we have 3 is given. Somebody offered us 3. Was that you, boss? Did you offer us 3?
Would it be 3, 3 to positive infinity?
3 to plus infinity. We don't include that. What do we do with this 3? Do we include it or do we not include it?
Include it.
Include it. So we put a bracket here.
Yeah.
Okay, so this 3 goes here. And if this value were less than 3, we would have a negative value under this root, wouldn't we? So it's got to be 3 or greater. 3 would make this a 0. Root of 0 is still 0. But if it were less than 3, we'd have a root of a negative value, which we're not allowing. Okay, and that works over here too, doesn't it? So x has to be
Yeah.
greater than 3, and that works here as well. So we'll say, here's our domain. Okay. Let's see, is there anything else we want to look at here? How about that's the domain of this? How about, what does the domain of this thing have to be? If I said the domain of F, that certainly works here. If I said the domain of G, how am I going to figure that out? What's the domain of G?
So similar to how we did for square root of x minus 3, you said the radicand expression, which is x plus 1. You know, I mean, you don't take the radicand. You just do x plus 1 equals 0, and then you solve for x.
And get x equals -1.
Yeah, and so the domain has to be -1 or greater.
-1 or greater. Okay, I'm going to thank Gopal for that. And I'm going to ask Gopal, now you've answered for everybody. I'm going to ask you to listen from now on, okay, and not provide answers because we know you know the answers, but we want everybody to have a chance to answer, okay?
Okay.
All right, so everybody, you understood what Gopal said there. So we're saying then the domain is going to be -1, and we're going to take that out to positive infinity. Very good. Okay. Let's see if I've got a different one here for you. How about if I am given, let's say I'm given the following. F of x equals 5x plus 6, and g of x equals 2x squared minus x minus 1. And I ask you to find the following. F of g of x. Now this isn't a multiply. This just says f of g of x. This looks like this. That's what this means. F of g of x. F of g of x. So in that situation, we're going to say, well, we're going to take f of x, and everywhere we find an x, we're going to put g of x. So we're going to say 5, and then where we have an x, I'm going to put g of x, 2x squared minus x minus 1 plus 6. Okay, that makes sense so far? Questions at all?
Yep, makes sense.
Okay. So if I now do my multiply, I'll get 10x squared minus 5x minus 5 plus 6. And this is 5x here, isn't it? 5 times this is 10x squared minus 5x. Okay, so 10 of the x squareds minus 5 of the x's, combine -5 and +6, we get a +1. Okay, so here is f of g of x. Okay, does that make sense to everybody what we did there? Any questions? All right, what if we go the other direction? What if we say, I want g of f of x? Go ahead and work that out, and then let's have a new volunteer step me through what this would look like. And we want everybody to have a chance to participate. If we were in class, I could call on people and see who's doing what. Here we're a little bit different. I'm just looking at names on the list here. So I can still call on names, but I'd rather just have you volunteer if you would. But I'd like to have multiple people volunteering so we all get a chance to have some fun. So g of f of x, we said that looks like g of f of x. So what are we going to look like here?
Okay, so we plug in the g of x.
Okay, so what would you like me to write?
Okay, so it is 5. And then the brackets, you have 2x squared minus x minus 1.
Like that?
Yes. And then you factor.
Factor?
Yes, 10x squared.
Is that factoring?
Oh, I'm sorry, just you multiply. I'm sorry.
We're going to distribute the 5 throughout this trinomial, aren't we?
Correct.
So 5 times 2 is 10 of the x squareds.
And
5 times negative is negative 5 of the x's, and 5 times this is negative 5.
correct.
Is that what you want?
Yes.
Okay. And that looks like what we got over here, doesn't it? 10x squared minus 5x. And let's see, what was different here?
It was a 6. It was a 6 minus.
Yes, we wanted a 6 out here, didn't we? We didn't.
Yes.
This g, let's see, 2x squared minus and plus 6 plus 6. So that's 10x squared minus 5x plus 1, which is the same as we got here.
Yep.
Is that what you wanted?
Yes.
Okay, everybody agree? Anybody disagree? What were we asking? The first one we were asking f of g of x. And the second one we're asking g of f of x. Okay, do we think those are going to be the same? Well, let's, this says take f of x and plug it in everywhere you have an x in the g function. Well, let's see, what was that g function? G of x equals 2x squared minus x minus 1. And f of x was, as we saw above, 5x plus 6. So everywhere we have an x here, we're going to plug in this thing. Correct? Everybody okay on that?
Yes.
Okay. G of x equals, and we said g of x is 2x squared, so that's 2. And then for x, we're going to put in 5x plus 6. We're going to square that. Minus x, which is 5x plus 6. And then minus 1. Okay, so g of x equals 2 times this thing squared. What's 5x plus 6 quantity squared? 5x plus 6, 5x plus 6, and we're going to FOIL that, aren't we? 5 times 5, that's going to be 25x squared. Outer is 5 times 6, that's 30x. Inner is 30x, so that's going to be plus 60x. Last is 6 times 6, so that's going to be 36. Minus this term, 5x plus 6, and then minus the 1. Okay, we all in agreement? So g of x equals 2 times this, so that's 50x squared, plus 2 times 60, 120x, 2 times 36 is 72, minus 5x, minus 6, minus 1. So g of x equals 50x squared, and then 120 minus 5, so that's plus 115x. And then plus 72 minus 7, 7 and 12, that looks like it must be 65. Okay, so it looks like we're at 50x squared plus 115x plus 65. Is that what was up above here? Is that the same as this? Are those equal? So when we did f of g of x, we put the g of x values into everywhere we found x in the f function, and we ended up with this. When we take g of f of x, we take the f of x function and put it in everywhere we find an x in the g function. Okay, and we came up with this value, which is not equal to this value. It's not equal to this value. These are two different values we get, aren't they? Everybody see that? Questions?
Just a quick question.
Yeah.
Did you not simplify it on purpose, or did you
Did,
just
did I do what?
did you not simplify it on purpose, or did you just
Not simplify? Did I not simplify what? I'm sorry.
I mean, can't we divide the equation by 5 and factor it out?
This here? This 5?
No, the bottom one.
Down here?
Yeah.
If you want to factor that out, what are you going to get? You want to factor out of 5? You can factor out of 5 if you want. Factor out of 5 and you get what? 10x squared? Plus, what do I get here?
23.
23 plus
13.
13. Okay, is that this?
No.
No.
Okay. Thank you.
Doesn't do us any good to factoring, does it? That's not something we would need to do. You wouldn't necessarily come up with something like this and factor it. You could, but you would generally leave it in this form right here. And this, my point is, the value we got when we took g of f of x, which is this value, that's this value here, is not equal to f of g of x, which is this value here. Two different values. We don't get the same value by taking f of g or g of f. They're two different functions. Questions? Okay. How about what if I give you f of g evaluated at -1 for that same function? So f evaluated at g, that's this one up here. And if we evaluate that at -1, so we want f of g, not of x, but at -1. Now what do we get? 10 times -1 squared, which is 1, minus 5 times -1 plus 1. So it's 10 plus 5 plus 1, or 16. So this function evaluated at -1 would give us 16, wouldn't it? Okay, questions? Okay. If there are no questions, let's say we take those functions and we want, let's see. Would be a good one here. Let's say we're given the following. Let's say we're given that f of x equals 4 divided by x plus 2. And g of x equals 1 over x. And we're going to do the same thing. A, find f of g of x. Okay, what do we think? F of g of x, f of g of x. So f of x looks like this. So that's 4 over x, but x is going to be g of x. And g of x is 1 over x, isn't it? So it's going to be 1 over x plus 2. All right, so that's the new material. That says we want to take f of g of x when we have quotients. And now we want to evaluate this. So let's see how good we are at doing that. And I'll rewrite that f of g of x equals 4. What do we do to this denominator here? We need some new volunteers to help us out.
Don't you multiply it by 1 over x minus 2?
Are you a new volunteer?
Yeah.
Okay. Multiply by 1 over x minus 2. So 1 over x plus 2, 1 over x minus 2. And now, before I do that, why are we doing that? I mean, we can do it, but I'm going to ask you why we're going to do it.
I don't know the exact answer, maybe just to cancel out the fractions, maybe.
To cancel out, will this cancel fractions if we FOIL this? First times first will give me what? 1 over x squared.
Yeah.
Now keep in mind, we're going to have to multiply the numerator by that as well, aren't we? So that
Yeah.
does that get rid of a fraction?
No.
And outer is going to cancel, and then last is going to be -4. So in the denominator, I'll have 1 over x squared minus 4. And in the numerator, I will have 4 times 1 over x minus 2, which is this value here. Is that what you want to see?
Yeah.
Okay, does that help us?
I'm
Is
be
that-
honest, I don't know. if
Is
it
that
does.
simpler? Okay. Any other thoughts? Does this help us, or do we have another method that we want to use? In other words, we're trying to simplify this thing here. So we're looking at now a new problem. We've done our substitution. We've used a new concept of f of g of x, where this is f of x and this is g of x. And we put the values in here. Now we have a new problem. We want to simplify 4 over 1 over x plus 2. So we can forget all the f of g of stuff. We just want to simplify. We just want to simplify this. So we want to take this denominator and we want a common denominator down here, don't we? The 4 over, and the common denominator looks like it's going to be an x here, and this is a 1. So we're going to have to multiply numerator, denominator by x, aren't we? So we'll have 1 plus 2x over x plus, well, nothing. It's just x in the denominator, isn't it? 1 plus 2x over x, right? They're both over the same x. Everybody agree? Now we want to invert and multiply this thing. And this 4 is really 4 over 1, isn't it? So we have 4 over 1 times inverting this and multiplying. We should have something that looks like that, which is 4x over 1 plus 2x. And can we go any simpler than that? Let's see. Well, we have 4, that should be an x there, shouldn't it? 4 times x is 4x. 1 times 1 plus 2x is that. So we end up with something that looks like that. And what is that? Well, that's f of g of x, which can be written f of g of x. And when we simplify it from what we had above, it becomes 4x over 1 plus 2x. So f of g of x, given that f of x and g of x, and we ended up with this value here.
Could you
Okay,
please
quick.
repeat how you got 1 over x plus 2x over 1x?
This value here,
No, like,
oh, here,
yeah, the one before that.
here.
Yeah.
All right, let's see what we started with. We'll rework this thing. F of x, we were given as 4 over x plus 2. That was the original. And g of x was given as 1 over x. And if we're asking for f of, do we want to solve for f of g of x? Is that what you'd like me to solve?
Yeah.
Okay. F of g of x looks like f of g of x. So f is this value. So there's 4 over x plus 2, but x is no longer x. It's 1 over x. It's g of x. So this goes here. So this becomes 1 over x. That's how we got that. So that shows how we get f of g of x is 4 over 1 over x plus 2. Okay, so far?
Yeah.
Okay, now we want to simplify this denominator as we did above. So it's 4 over 1 in the numerator. Denominator, we want a common denominator down here. So I'll multiply and divide by x. So I get 1 plus 2x all over x, isn't it? The common denominator is just x. And then I invert and multiply, and I get 4 over 1 times x over 1 plus 2x, which is 4x over 1 plus 2x, which is what we had here.
So when you multiplied 2 by x over x, don't you have to multiply 4 also?
Down here, you're talking about this?
Yeah.
Okay, let's make this a separate problem. So this is 4 over something, and we're going to make this something a separate problem. So we have 1 over x plus 2. That's what we started with. 1 over x plus 2 was the denominator. And I'm saying we can't combine these two values, 1 over x and 2. We can't combine those unless we have a common denominator, right? We can't combine 1/2 and 2/3 until we have a common denominator. So to get a common denominator, I have an x here, so I need an x here. So I'm going to put an x there, multiply x times 1 gives me the common denominator. But if I multiply denominator by x, I also have to multiply numerator by x. So now I get 1 over x plus 2x over x. And when I combine those, what do I get?
2x plus 1 over x.
X plus 1 over x, like that.
No, I mean, sorry, I meant 2x plus 1 over x.
2x plus 1 over x. Okay. That's what we had here, isn't it?
Okay. So we didn't have to multiply 4 by the x because we multiplied 2 at the bottom with x.
Yeah, we're working just with the denominator.
Okay.
And when in order to combine these two terms in the denominator, we had to have a common denominator, which was x. So we simplified the denominator and called it 2x plus 1 over x. That's what the denominator was. That's this. And we had 4 over that thing. So now we continue to simplify by inverting this and multiplying, which is what we did here. So we had 4 times inverting this and multiplying x over 2x plus 1. Here's the invert and multiply this, the numerator. Here's the numerator. So that gives us 4x over 2x plus 1, which is what we had here, which is what we had here. So what we're doing down here, this business of simplifying this stuff, this is our math, what, 97, 98, 99. We're no longer doing f of g type stuff. We've already done that substitution. And now we're doing straight algebra. Okay, this is no longer pre-calc. This is just straight algebra. How do I combine 1 over x plus 2? And we can go back and look on our Math 97 book, I suspect, and find out how we do that. And we do that by multiplying numerator denominator by x and get 1 plus 2x over x. And then we say, well, hold it. That was the denominator of something else. It was the denominator of this thing. So how do I simplify that? Oh, I invert and multiply. Okay, so that becomes 4x over 1 plus 2x. So we had to do a couple of operations, but these are just algebraic operations, where this was the pre-calc operation up here, this f of g of x.
Okay, thank you.
Sure.
I have a question about the homework.
Yes.
So it is problem 49 on the 1.8.
1.8, 1.8. We're doing 1.6 and 1.7 today, not 1.8.
Okay.
1.8 1.8 we cover on Monday.
Okay, thank you.
Homework is 1.6 and 1.7.
But it's only one problem though. I just worked ahead a little bit.
All right, see me after class, after we stop the class. We
It
will,
stops what time? 7:10. I mean 5:10, right?
5:10, yep.
Thank you.
I have a question on
Yes.
the syllabus. It says that we don't have class on Monday.
We don't have class on Monday. Let me see. I don't know why it would say that. Does it say the 25th, no class?
Yes, it
That's-
says 10:25, no class.
No, that looks like it must be an error. I don't know why that would. There's nothing on my calendar here, and there's nothing on the calendar here. So I'm going to take a note and change that. I don't know why I would say that. So 37. So it was in the syllabus.
Yeah, it's on the main page on your Canvas on the, yeah.
Page 1 on Canvas. Okay.
Yeah, as soon as you go to it.
Okay. I will make that change. I don't know why it would say that. It's, yeah, 1025. We're covering 1.8 and 1.9.
It's possible that that carried over from a different quarter, professor, like
That could be.
or a previous year or something like that. But
Yeah.
it definitely says that for week 5, 1025, no class.
Yeah, I will make that change as soon as we're done here.
So we have homework 1.6 and 1.7 due on Monday.
Yes, that's correct.
Okay.
So on the syllabus, the homeworks are also different than what you're assigned. For example, it said that we covered 1.4, 5, and 6, I believe, on Monday, even though we only did 4 and 5.
All right, I'll go. Where is that showing?
On the syllabus,
Canvas syllabus.
yeah.
All right, does it show? Well, yeah, the syllabus doesn't show homework. It's the schedule that shows the homework, right? This schedule is what shows our homework.
Yeah, professor, it is the version of that schedule that you have pasted to the syllabus, but I recommend that everyone in class that has questions about that, take a picture of what you have up on your screen right now, because that is the most up-to-date information. Don't trust what you see on Canvas right now.
I'll see if I can erase that from Canvas. I'm not sure why I pulled that up. I'll take that off of Canvas. Yeah, your homework is 1.6 and 1.7 due Monday, the 25th. And on the 25th, we'll cover 1.8 and 1.9. Okay, other questions? All right. Go ahead.
So I turned in my I think homework for 1, 2, and 3 yesterday, and I was just wondering if you got it.
If I get it, I will check it off. Your name is what?
Ruthie.
you turn in 1, 1, 1, 2, 1, 3, right?
Mhm.
Yeah, I have it checked off.
Okay, thank you.
So is class done?
We are done. Yes, we're done at 5:10.
Thank you for the lecture, Professor.
Sure.
Hope you have a great rest of your day and enjoy your weekend.
Yeah, you too. And somebody had a
Thank you.
question on one of the
Have a good day.
problems.